Welcome to Ready to Derive. In this video, we learn the rules for taking the derivative of the product of two functions and the quotient of two functions, called the Product and Quotient Rules, not very imaginatively. While the formal proof of both rules will be treated in a separate video, I do try to provide an intuitive approach to understanding the genesis of the product rule. So not too much theory in this video, but lots of practice. Let's get started. So I'm going to begin by clarifying what the product rule is not. And this is important because this mistake is easy to make, and I like to sort of clear it up, get it on the table before we even dive into the product rule. So we know from a previous video that the derivative of a sum of two functions is, as we would hope it would be, just the sum of the derivatives. And also the difference, the derivative of the difference of two functions is the difference in the derivatives. So you would hope that maybe the derivative of the product of two functions would be the product of the derivatives, which we might write like this. This is not the case. And so I almost prefer if you didn't even take these notes down, just so it's not ingrained in your mind. So this is not the case, but it's an easy mistake to make. And let's see why it's not the case. Let's use a demo example. So here we have a product of two functions. Now we know that to find the derivative of this, it's just easiest to sort of FOIL out. So if we FOIL that out, x cubed minus 5x squared plus 3x minus 15, then we can use the power rule. And we get that the derivative is 3x squared minus 10x plus 3. Now let's just pretend that we decided to do our illegal shortcut, what we would like the product rule to be, which is that you just take, if that's f of x and that's g of x, you just take the derivative of f of x, which is 2x, and you multiply it by the derivative of g of x, which is 1, and the answer is 2x, which it's not. So we can see that this very easy conceptual mistake to make is to be avoided at all costs. So now let's look at what the product rule actually states, which is that the derivative of a product of two functions is the derivative, say, of the first function, we'll call that f, so f prime x times the second function, plus the first function times the derivative of the second function. And that's nice and symmetric, and every function gets its time in the derivative limelight, and it makes sense that it's symmetric because multiplication is commutative, so the formula shouldn't change just because you change the position of f and g. So while I'm not going to prove it in this video, that's going to be done in another video because it's very time consuming, I'm going to sort of show you using area how this intuitively, this rule makes sense. So let's take this rectangle and call that side u and that side v. So the area of this rectangle is u times v. And what are u and v? I'm going to make u be f of x, say, and v be g of x. So the product of those two functions is really just the area of this rectangle. And to talk about the derivative of the area is to talk about how fast the area is changing, what rate the area is changing for a small change in x. What effect does it have on the area of this rectangle instantaneously? So if we think about making a little change in the value of x, well, that's going to make a change in u and a change in v differently. du and dv are going to be different because f and g are different. So what does that look like? So if we make a change in x, then we are going to, in effect, say we increase x a little bit, we're going to change u by an amount delta u. And we are also going to change, we're going to increase the length of this side by delta v. I mean, they could be decreasing, but I'm showing increasing for simplicity. So this little change here is going to be the change in v. So we have a slightly larger rectangle. Oh, we're missing a piece. We also have this little yellow piece right here. So that's our new rectangle after a little change in x affecting a change in u and v. So we could talk about the change in the area at that moment. So the change in the area is going to be whatever the area of the green rectangle is, which is actually, let's see, its width is delta U, and its height is, well, it's just the same as V, plus the area of the red rectangle, which is U, is its length, times delta V, plus the area of that little yellow rectangle, which would be delta U times delta V. Now, as delta x goes to 0, so as, remember, because that's instantaneous rate of change would mean delta x goes to dx, which is tending to 0, this product here is going to go to 0 itself, because the change in u and the change in v is going to be so small that it's negligible. So we get left with, if we think about it, so as delta x goes to, often we write delta x becomes dx. It's more symbolic representation at that point. So d, the little change in u times v, is going to be just du times v plus u times dv. And then all we have to recognize is that this was always with respect to x, with respect to a tiny change in x. And there we get the product rule. So du by dx, or the same as f prime. So this is really just f prime. This is really just g prime. V, that is g, and that is f. So it's the same rule. Now, actually, I prefer to use u and v, so I'm going to like sort of condense that and write the product rule as this. And it's easier to use u and v because quite often our product function is expressed as f or g, and it starts to get a little confusing. So moving forward, we'll be using the formula as written in the yellow box. So let's revisit the function that we began the introduction with. We found the derivative of this by distributing, foiling out, and then using the power rule, and now we're going to use the product rule. So in order to do so I'd like to kind of start out by identifying u, v, and u prime, v prime. So u is the first function, x squared plus 3. It could be the second, but usually just start with the first. So u prime is 2x. And v is x minus 5, so v prime is 1. And then we call up the product rule, and we realize, okay, so now to use correct notation, we're finding dy by dx. And so we start with u prime v. U prime v is this product. Kind of got a nice diagonal thing going on there. So it's 2x times x minus 5 plus, and uv prime is the other diagonal. So there we have x squared plus 3 times 1. And if we distribute 2x squared minus 10x plus x squared plus 3, and then rearranging and simplifying, we get 3x squared minus 10x plus 3, which is what we got when we FOILed and did the power rule the proper way. So here is an example that the product rule really works. So in this example, here's a function that we could not find the derivative of without the use of the product rule, because there's no foiling here or expressing it in another way. We have to use the product rule. So let's start by establishing u and v. Now, you might as well put the 5 with the x, so u is 5x, and v would therefore be sine x. So that's u, that's v. The derivative of 5x is 5. The derivative of sine is cosine x. Call up the product rule. Notice I've kind of left out the little, I'm simplifying it every time. Before I had little multiplication symbols there, now I don't, because as you write the product rule over and over again, it's nice to just condense it as much as possible. So in this case here, we have f prime x, and we want u prime times v again. So nice to kind of look for that diagonal. So u prime times v, so that's 5 sine x plus, and then u times v prime, which is 5x times cosine x. And we're done. It was that simple. Now, sometimes, if that x wasn't there, so say we had had f of x equals 5 sine x. no need, while you could do the product rule here, so you could make that u and this v, it would be kind of a waste of time because 5 is just a constant. So you only really need to use the product rule when you see x appearing in two or more places, as we will see in the next example. So if f of x was just 5 sine x, and f prime x would have just been 5 cosine x. No need to waste your time with the product rule in that case. So in this function, we actually have x appearing 3 times. So let's see, let's put this in green. So we have one function there. Let's make u 5x, and v can be sine x. And then we have, let's see, e to the x. Let's make that w. So we have a product of 3 functions. Our product rule only works with 2. So we're going to have to come up with a formula for 3 functions. Well, we can do this by dividing into 2. Let's call the first function uv and the second function w. And the product rule says take the derivative of the first function. I'm going to write that like this for now, times the second, plus the first function times the derivative of the second. And now we get to use the product rule again for this portion, because let's put that w out there. The derivative of the product will be u prime v plus u v prime. And let's not forget we have u v w prime here. And distributing out, we have u prime v w. So look at that, the derivative of the first function times the second 2, plus the derivative of the second function times the other 2, plus, to be fair, the first two functions times the derivative of the third. So we can actually, now that we have it, really makes sense. It's nice and symmetric. You can see how this would apply to the product of 4 or more functions, and it's very easy to generate. So if we want r prime x, rather than writing u, v, and w all out, we just go in stages. So the derivative of u would be 5, and then times sine x e to the x, plus 5x times the derivative of the second function of sine x is cosine x, times e to the x, plus 5x sine x times the derivative of the third function, e to the x. And there's your answer. You could leave it like that. Then there's no like terms or anything, but if you wanted to tidy up a bit, you could take out 5e to the x, and you get sine x plus x cosine x plus x sine x. So now for the quotient rule, the derivative of a quotient of 2 functions. As with the product rule, this is not equal to f prime over g prime. Don't make that mistake. In fact, it's such a bad mistake to make. I'm just going to erase that right now, and let's get into what it really is. So it's sort of similar, starts out looking like the product rule. You take the derivative of the top function times the bottom. That looks very product rule-like. You also are going to do f times g prime of x. So the product rule, if we put a plus between there, that would be the product rule. But the quotient rule says we have to subtract these quantities and then divide by function in the denominator squared. So the proof of that is more elaborate, to be treated in another video, but so for now, just want you to remember the quotient rule in the condensed form. So the derivative of u over v is u prime v minus uv prime all over v squared. So let's apply the quotient rule. Here we have a quotient. Remember, u is the upper function. That's u for upper, and v is the one in the denominator. So u is e to the x, v is x squared plus 1, du by dx, or u prime is e to the x, and this is 2x. And this is what the quotient rule says. So dy by dx will equal u prime v. So once again, it's that diagonal. So e to the x times x squared plus 1 minus, don't forget that minus, e to the x times 2x all over v squared, which is x squared plus 1 squared. And to tidy up a little, sometimes this is useful, especially if you have to use the derivative for any other reason. We're going to take out e to the x. So I see it's in both terms, so I'm going to take that out over x squared plus 1 squared, and I might even take it one step more. There's much more than we really have to do for this problem, but by factoring that quadratic, you actually get dy by dx in a form where it'd be useful for finding, say, where there are horizontal tangent lines of this function, because it's in fully factored form. So for our last practice problem, we're going to treat a function whose derivative will involve both the product rule and quotient rule being used, just for a more complicated scenario. Okay, so we have to find the value of r prime 1. We're given this information about g, and then we are told that this is the graph of f. And since it's all happening at x equals 1, take a moment to realize that the two facts that we know from this point at x equals 1, the first of which is that f of 1 equals 3. That's just the y-coordinate where x equals 1. The other fact is f prime at 1. That would be the slope of the line there. And we can see that the slope is -1 right there, right? Because it's down 4 over 4, or down 1 over 1, even from coming here, down 1 over 1. So given that fact, let's set up our structure for the quotient rule. Now, instead of just calling it u equals, I'm going to actually say u of x equals, in this case, let's go back to this, x squared f of x. And that's the upper function, and the lower function is just d of x. And the reason that I'd like to do that is because from this point, I can also figure out what u of 1 is. So it's going to make my quotient rule entry a little easier. So u of 1 would be 1 squared times f of 1. We just realized that f of 1 is 3 from the graph. So therefore, it's 1 times 3, which is 3. And we can also figure out that v of 1 is just g of 1, which is given to us, it's 2. So now, what about u prime x? Well, notice here that we actually, to take the derivative of that, we're going to have to use the product rule. So the derivative of x squared is 2x times the second function, plus the first function, x squared, times the derivative of the second function. And this allows us also to find u prime 1, which we will be using. So this would be 2 times 1 times f evaluated at 1, plus 1 squared times f prime evaluated at 1. And once again, we know that f of 1, again from up here, is all we need. F of 1 equals 3, and f prime of 1 is -1. So we know that this is 2 times 3 is 6 minus 1 is 5. And v prime x would just be the same as g prime x. So therefore v prime 1 equals g prime 1, which we are given up here, is 1/3. So now I'm going to pull up the quotient rule, but with 1 input as the value of x, so that then I can just use these values to make an easy substitution. So u prime of 1 is 5 times v of 1 is 2 minus u of 1 is 3 times v prime of 1, which is 1/3. And let's not forget to divide by v of 1, which is 2 squared. If we work that all out, we get 9/4 as the answer. So once again, this structure, doing sort of all the work in this table up ahead, makes the actual use of the quotient rule much more efficient. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.